The sound of a steel wheel slamming against a steel rail is the heartbeat of global civilization. For 2 centuries, trains have been the ultimate heavy lifters of humanity. But beneath the roaring engines lies a fierce evolutionary battle of physics, thermodynamics, and electromagnetism. Welcome back to Machinery Explained. If you want to master the hidden mechanics behind the world's most powerful machines, hit that subscribe button and drop a like right now. Today, we are breaking down the entire evolutionary tree of trains, from the smoke-belching monsters of the past to the gravity-defying speed demons of tomorrow. 1. The pioneers. Steam locomotives. We begin in the 19th century with the machine that sparked the Industrial Revolution, the steam locomotive. These are pure mechanical brutes. The engineering relies on a massive internal boiler. Coal or wood is burned in a firebox, heating water until it flashes into high-pressure steam. This steam is forcefully directed into cylinders, pushing heavy pistons back and forth. Through a system of rods, that linear movement is converted into rotational force to turn the massive driving wheels. While visually majestic, steam engines are wildly inefficient. They lose over 90% of their thermal energy to the atmosphere and require constant stops for water. By the mid-20th century, their fires were permanently extinguished by a more efficient beast. 2. The heavy lifters. Diesel-electric. Look at any massive freight train today, and you are looking at a diesel-electric locomotive. A common misconception is that the diesel engine directly turns the wheels. It doesn't. Instead, a monstrous, multi-thousand horsepower diesel engine acts purely as an onboard power plant. It spins a massive alternator, generating thousands of volts of electricity. This power is sent down to intense traction motors mounted directly on the wheel axles. The physics of steel on steel, a loaded freight train can weigh over 10,000 tons. If a diesel engine were mechanically geared directly to the wheels like a car, the sheer weight would shred the transmission instantly on startup. Electric motors provide maximum torque at 0 RPM, allowing them to move massive loads from a dead stop. 3. The urban lifelines. Electric and commuter trains to move millions of people through tight urban corridors without choking cities in smog. We strip the power plant off the train entirely. Electric locomotives pull their energy directly from the grid. They collect power using a rooftop frame called a pantograph, which friction rides against high-voltage overhead wires or via a third rail running alongside the track. Because they don't carry heavy fuel or massive engines, electric trains are incredibly lightweight, accelerate instantly, and produce 0 localized emissions. They are the backbone of subway systems, light rails, and commuter networks worldwide. 4. The speed demons. High-speed rail. When you push conventional trains past 150 miles per hour, standard rail physics begins to break down. High-speed rail systems, like the Japanese Shinkansen or French TGV, require entirely re-engineered infrastructure. At extreme speeds, tiny bumps in traditional wooden-tied tracks can cause catastrophic derailments. Therefore, Hissar runs on continuously welded steel rails laid on massive, unyielding concrete slabs. The trains themselves are highly aerodynamic to slice through intense air resistance. They utilize distributed traction, meaning electric motors are spread under multiple passenger cars rather than relying on a single locomotive at the front, balancing weight and maximizing stability. 5. Defying gravity. Maglev. To break the ultimate speed barrier, engineers had to eliminate the 2 biggest enemies of velocity: mechanical friction and track wear. The answer is Maglev magnetic levitation. Maglev trains have no wheels, no axles, and don't technically touch the ground. Instead, they use 2 sets of powerful electromagnets. Without wheel friction, Maglev trains routinely blast past 370 miles per hour, making them closer to wingless airplanes than traditional railway cars. 6. The Cargo Kings. Freight and intermodal while passenger trains get the glamour. Freight and intermodal trains keep the global economy alive. These are the logistical titans of the rails. The true genius here is intermodal shipping. Trains pull miles of flat cars loaded with standardized shipping containers that can transition seamlessly from cargo ships to rail cars and straight onto semi-trucks without ever unpacking the goods inside. To handle extreme weights over mountain passes, railroads use distributed power, placing remote-controlled locomotives in the middle and rear of the train to push while the front locomotives pull, preventing the couplings from snapping under tension. 7. The Unsung Heroes. Maintenance of way. Tracks don't stay perfect on their own. Under the brutal, continuous pounding of multi-ton traffic, the stone foundation called ballast shifts and steel rails warp. Enter the maintenance of way fleet. These are highly specialized, bizarre-looking mechanical monsters. Ballast tampers use massive hydraulic claws to pack loose stones under the ties to level the track. Rail grinders use a sequence of spinning abrasive wheels to reshape the worn profile of the steel tracks, correcting microscopic cracks before they turn into fatal fractures. Without these machines, the entire rail network would grind to a halt within months. From the boiling water of the first steam engines to the invisible magnetic fields lifting modern maglevs, the evolution of the train is a masterclass in human ingenuity. Every type of train is a precise engineering solution designed to conquer friction, maximize efficiency, and move humanity forward. Thank you for watching this deep dive into the grid of the rails. Which rail system blows your mind the most? Drop a comment below, invest in your knowledge by subscribing, and we will see you in the very next mechanical breakdown right here on Machinery Explained.